Thanks for taking the time to watch this video. Just a note that if you're ever interested in any private one-on-one tutoring, I do offer that service. You can contact me at this email address, and we can arrange a virtual meeting through Google Meet or through Zoom. So now on to the problem here. We have a stock solution of 14.8 molar ammonia. So that's the stock solution right here. We know the molarity of that stock solution. We're actually just going to call that molarity M1. So M1 is equal to 14.8 molar of NH3. But what we want to do in this problem is we want to extract a certain volume of it. So imagine that little bubble right there contains a certain volume of the stock solution. That would actually be V1. We don't know that volume yet, but just imagine taking that volume of the stock solution, whatever it might be, and transferring it over into this other container here. So now that volume would be over here. And then imagine taking some water and filling up the beaker until it reaches a final volume of 100 mils. So what that would do is it would dilute the solution. It would dilute it into a lower molarity, and that diluted molarity is 0.25. So we know that the molarity in the second vessel is going to equal 0.25 molar of NH3. And we also know that the volume of that solution is going to be 100 mils. What we don't know yet is how much volume to extract from the stock solution. So that's V1, and that's what we're going to be solving for. Now, how do we do that? Well, what we have to understand is that however many moles we take out of the stock solution, so imagine that there's some moles of NH3 inside that little orange bubble, we're going to extract it. We're going to pick up those moles and we're going to move it over into the other vessel. But of course, hopefully you can see that however many moles we take out of the stock solution would be the same as the moles that we put into the diluted solution. So basically moles equals moles. So we could say that the moles from the stock solution would equal the moles from, or the moles inside the diluted solution. So moles are conserved. But moles are equal to the molarity multiplied by the volume. And in order to see why moles are equal to the molarity times the volume, just look at the dimensions. So molarity is measured in moles per liter. Volume, in a standard unit, is measured in liters. So if you multiply molarity by volume, then the liters cancel, and that gives you moles. So moles could be represented as molarity times volume. Now we're looking for V1, so we're going to solve the equation for V1 by dividing both sides of the equation by molarity 1. This will cancel the molarities on the left side, and that gives us our final arrangement. We can actually go ahead and plug in the numbers at this point. So there are the numbers plugged in. You can see dimensionally that molar will cancel out because you have molar divided by molar, which is just 1, and then you're left with the target unit of mils. When you compute this, you will see that V1 is around 1.69, and then that again is in milliliters. And that is the volume that we must extract from the stock solution and then dilute up to 100 mils to achieve this target solution of 0.25 molar NH3. So again, the answer is 1.69 mils. We do have a part B. It says if you take a 10 mil portion of the stock solution and dilute it to a total volume of 0.25 liters, what will be the concentration of the final solution? So as you might know by now, this is a very similar procedure. They're just kind of changing it up a little bit. This time we know how much volume we're extracting from the stock solution. We're going to be taking a 10 mil portion. Excuse me, I wrote down the wrong volume. Let me fix that. So we're taking 10 mils from the stock solution. We're going to transfer it over into this beaker, fill in some water until we get a final volume of 0.25 liters, and then we want to know what that final concentration is, what that M2 is. And of course we can use the same formula. We're going to have to be a little bit careful with the units, as we'll see in a moment. But let's write down that formula again. This time we're solving for M2, so let's go ahead and divide both sides of the formula by V2 so that the V2's cancel on the right-hand side. So this would be our final version of the equation, but where we need to be careful again is with the units. So if you start plugging in, you'll have 14.8 molar for M1. The V1 is 10 mils, but then watch this. If you naively just come in here and plug in 0.25 mils for the V2, well, then you have some inconsistency here in your dimensions. You have milliliters. Goodness gracious, this should have been liters, excuse me. We have some inconsistency here, milliliters on top of liters. That's not good. You don't want that because those won't cancel. So you have to either change the mils into liters or the liters into mils. You'll get the same answer either way. So let's just take a little aside. Let's take the 0.25 liters and let's change it into milliliters. Now, hopefully we know that 1 liter is 1,000 milliliters. So if we multiply by that so-called conversion factor, the liters cancel, and then you end up with 250 mils. So make sure you change that volume into mils. We'll write 250 mils. This time we have dimensional consistency. The milliliters will cancel out. Let's pick up our calculators and compute this. And when we do that, we get 0.592. The unit that's left standing is molar. That makes sense because we're calculating a final concentration, so it should be in molarity. Notice it is more dilute. The original stock solution was 14.8 molar. The diluted solution is 0.592 molar.